1 minus V dot U, where there's a green dot product, all squared, and then there's a green quadrants of V times the green quadrants of U. So the same formulas. That means the understanding, the laws that we're going to develop, that we have developed, they're going to apply in these red and the green situations almost without having to make much adjustment. That's a fabulously important thing. That means we can do relativistic geometry pretty well in the same breath as we do standard Euclidean geometry. There's a massive unification of planar geometries. Okay, so try to overestimate the importance of this point of view. Okay, three basic formulas, all pretty much the same for defining spreads between two vectors. Blue spread, red spread, green spread. Okay, let's write down explicit formulas so we can see exactly what these spreads look like. So let's take the vectors V, D, A, B, and U, D, C, D. Okay, those are our two vectors. Then the blue spread between them, well, there's the expression that we've written down before. Those are the blue quadrants of the vectors. Then this dot product over here is just AC plus PT. So this is the expression for the spread between these two vectors. 1 minus AC plus PD all squared over A squared plus T squared times C squared plus D squared. And correspondingly, the red spread, a very similar formula, with the difference that here there's an AC minus PD, that's red dot product squared, and here we have the red quadrants. And in the green situation, same kind of thing, except now we have the green dot product, which is AD plus AC, all squared in the numerator there. And on the bottom here we have the product of the two quadrances. Green quadrant of this vector is 2AB. The green quadrant of this one is 2CD. And so the product is 4ABCD. Now when we compare these things, I mean, it's interesting because we said that this is a Euclidean situation, that these are relativistic. But you can see that there's some kind of brother-sister relationship between the blue and the red ones. They are pretty closely related. They look almost the same. This is a plus sign turning into a minus sign. The green one, however, looks quite a little bit different because, well, first of all, that's a little bit different, but the denominator especially quite different. In some ways, the green one is simpler than these ones. If you have to calculate this for a lot of vectors, you might very well prefer to work with this one rather than these ones. That's a curious kind of phenomenon that occurs in Chromos geometry, that even though the red and green are both sort of relativistic geometries, so quite a lot different geometrically from the blue one, nevertheless the green one is often easier to compute with. That's actually can be a pleasant thing that one can actually exploit, because calculations in the green geometry are often simpler than they are in the blue or the red situations. But you may say, wait a minute, didn't we have this other formula for the blue spread? In fact, we did. That was the whole point of connecting things with determinants. So remember that in the blue case, we have our familiar two vectors here. This spread formula has this alternate formulation. It's a different expression from this one, but algebraically equivalent to it. This expression has the AD minus BC term in the numerator squared, and still the product of the quadrances in the denominator. So here is the cross product expression. That's not one of the three bilinear forms, it's the cross product. That represents, as we see, the area or the side area of the parallelogram spanned by V and U. So this expression relates the blue spread directly to the normalized squared area of this associated parallelogram. That's what we saw in our last video. Very powerful understanding. And that's an interpretation of what the spread is. It's basically an area squared, which is normalized to take account of the fact that it shouldn't really depend on the sizes of the vectors, just their directions. So that's the question. What about the red and green spreads? Do they also have some kind of reformulation like this one? Well, so of course the answer is yes, there are equivalence formulations, and here they are. And I'm going to leave the derivation of them, or maybe when you say the verification of them, to you as an exercise, just some basic algebra. So the story is again that we have vector V plus AB, and U which is CT, and here is the expression for the red spread. Here's the familiar one that we started with, that's really the definition, and now here is this alternate formulation of it, okay, which looks a lot like the reformulation of the blue one. We have an AD minus BC, the same determinant aspect or cross product in the numerator as we did in the blue situation. Still squared, and still the product of quadrants is there. But also in addition we have this negative sign. What happens in the green situation? Well, there's the definition of our green spread, and then I'm claiming that this thing actually algebraically turns out to be this thing. So again, it's a very similar kind of story. We have the AD minus BC squared up on top, and somewhat familiar 4ABCD, that's the product of the quadrances in the denominator. But again, there's also a minus sign. So the fact that these two things are equal is another identity, very similar in the same kind of direction as the identity due to Fibonacci or Diophantus in Alpha Factor that was responsible for things in the blue situation. But now there's sort of a red version of that identity, and it's going to be a green version of the identity. So the fact that this equals this, it amounts to a certain algebraic identity, and it's useful for you to write out and just check that that's actually working. So it's very pleasant. We have the determinants, which are these signed areas, appearing here just as we did in the blue situation. So these are still basically normalized squared sine areas, with the small proviso that there's a little bit of something else happening because of those minus signs that are appearing for some reason or another. Okay, so but let me remind you that although these formulas are a little bit different from the blue formula, because of the minus signs, the actual definitions of the spreads are exactly parallel without any modification whatsoever. Okay, so please check the validity of these expressions, and in our next video we want to have a look at the geometrical meaning of these things. What does it mean to consider a red spread between two vectors or a green spread? What's the relationship between these spreads? And we want to then move to an even broader understanding where we maybe even transcend this threefold symmetry and look at the general situation, okay, which maybe will explain or shed some light on where those minus signs are coming from. So I hope you'll join me for that. I'm Noah Lawberger. Thanks for listening. I'm Noah Lawberger. In today's video, we are going to solidify our understanding of the spread between two vectors. We have seen that this is intimately connected with the notion of determinant, which expresses the area of a parallelogram. Today, we want to connect this with linear algebra and move towards understanding this beautiful threefold symmetry called chromogeometry, which lies at the heart of planar geometry. Okay, so here's what we have discovered so far. That if we have a vector v, which is AD, and a vector w, which is CD, then the spread between them, this S here, can be expressed with this formula here. It's AD minus BC all squared over the product A squared plus B squared times C squared plus D squared. What's in the numerator here, this AD minus BC, is just the area of this parallelogram, actually the signed area of this parallelogram. And we introduced the idea of a cross product in the planar situation. We said that this number can be regarded as the cross product between V and W. That's a very useful kind of thing that's a little bit different from the three-dimensional cross product. It's a number then that's associated to two vectors, which just tells you what's the area of the parallelogram that they span. Now, the fact that this is a sine area doesn't really figure because we end up squaring it, so we end up with something positive in the numerator anyway. And the quadrances here are in the denominator, so that's kind of a normalization. So geometrically what we're doing is we're taking these two vectors and we're looking at this parallelogram, taking the square of its area, and we're dividing that by the product of this square area and this square area. Okay, so it's really a normalization of a squared area. In fact, it's geometrically perhaps the simplest kind of number that you can associate to two vectors, which ended up not really depending on the scaling factors. If you scale the vectors v and w, then this quantity does not change. The quadrant, of course, is a fundamental concept in rational trigonometry, and we can also interpret it here as also a cross product between vector v and what we might call v super v, which is the rotation of the vector v. So if v is ab, then v super v is minus dA, and that's a rotation by a quarter of a turn. So typically this is v, then v blue would be up in this direction here. And I'm drawing the square on this side, but it's probably actually a little bit more honest if I drew it like this, but then it would overlap the current diagram. So the W, same story, the W is there, the WD would be this vector here, so we'd be talking about the area spanned by this W and its blue rotation. So very nice formulas, and we want to look more carefully now at the nature of this expression, and then ultimately move to the red and green versions of it. So it's a very big step in 21st century mathematics to move from considering angles to considering spreads. Absolutely very crucial development. And let's have a look at how this spread is such a rich concept by seeing algebraically that it's full of life. So here's this quantity that we talked about that was just defined, and here is a very important fact about it that we've seen before, but it's well worth repeating. That it can be rewritten as 1 minus the fraction AC plus BD squared over A squared plus B squared times C squared plus D squared. Now what's appearing in the numerator here is also a kind of product of the vectors, but it's different from this cross product. This is called the dot product between two vectors. So here it is right here. V dot W, so the dot product between the vector AD and the vector CD is this quantity AC plus BD, the product of the two first entries plus the product of the two second entries. So it plays a very, very important role in linear algebra because it naturally generalizes so plentifully to higher dimensions. Now this identity here is a consequence of what we might call Fibonacci's identity, which is this relation here. So if you take everything over a common